Okay, so I've just loaded the HPV model version 7. Now this is a model which riffed off of a larger model contributed by Merck, as I recall, on HPV. And it illustrates a couple of features, and these features relate to something Vicky asked earlier. And I'll just highlight two things. So we have a male and a female component of this model, okay? The male component is rather simple, okay? And you'll notice as we're browsing this, you'll see something kind of strange. I'll explain it in just a minute. You'll see some background images beneath it. But here's a male progression from HPV states: vaccinated, susceptible, infected, immune. And within each of these states, ladies and gentlemen, you have some contact going on and some progression. So here we were interested in understanding the spread of HPV and the impact of various types of HPV vaccination. For example, one project I'm working on right now, quadrivalent and nonavalent vaccines, and look at their relative impact. So we have male with a quite simple representation. Let's zoom out of that and let's look at female. Okay, female you'll find to be rather more articulated, and this reflects, unfortunately, the burden of risk of cervical cancer. Okay, so we have all these different states as delineated by the Merck model. The Merck model is a compartmental model, and we turned it into an agent-based model with comparable rates. These are exponentially distributed, just like rates in the original model, captured via compartments. Okay. Now, an important feature of this model is that we have individuals rather than compartments. And as a result, we can assort people into networks, right? We can place people into networks with each other. And, yeah, question?
I noticed that you have almost three-dimensional.
Yes, and I'm going to show you that in just a second. So one of the things we did in this model, it's a little bit different, is, and this relates to Vicky's question, we had additionally, beyond male and female, we had a general characteristics of a person that are shared by both males and females. Here, smoking status and sexual activity group, risk group, and then some ages. And we kept track of ages. This isn't the only way to do it. As you know, we can keep track of continuous age, but we did it in this way. I know it ain't pretty. We did it in these age categories because these are the categories maintained in the Merck model. Okay, you'll notice that they are not uniform: 0 to 4, 5 through 9, 10 to 11, 11 to 12. For the teenage years, particularly in young adulthood, we have greater resolution, as befits the burden of HPV. Now, the point is that this is for person as a whole, and male and female are also persons, okay? If you go look at female, for example, the definition of female class, this, if you scroll down to the bottom of female, this extends, excuse me, this was done in an earlier version of AnyLogic, and it's actually become easier since the very first version where we experimented with this, but this extends another agent. What that means is anyone who's a female is also a person. So all of these characteristics of person that you see applying also apply to male and apply to female. So we don't have to duplicate this functionality separately for males and females. So let's imagine a situation like Vicky mentioned. Let's imagine a situation where you have a population, and you have some population members who are healthcare workers. And those healthcare workers come in various varieties. There's doctors and there's nurses, and perhaps doctors themselves come in a certain varieties, infectious disease doctors and otherwise, and nurses, or include public health nurses and otherwise. And so you have this hierarchy of specialization. You know, everyone's a person, and are subject as such to certain risks of infection and certain behavioral patterns, etc. They have a home, and they have certain work schedule, and they go back and forth to home, etc. But then there are subtypes of individuals who also share certain more specific characteristics. So healthcare workers perhaps have a certain duty to serve under certain conditions. Doctors will have certain roles vis-a-vis interacting with patients that are different from nurses, and nurses' roles may expose them to greater risks of contamination.
You're getting into gender.
Not necessarily.
No,
the
no,
nurses
but in a
could.
sense you are, because you're taking into account roles. So
Well,
you're going beyond male, female.
That's true. That's true. Yeah, I mean, there's role-specific risks, right? Absolutely. And I mean, in some of the burdens we see with TB in our work, there's high risk certainly among women, and there's conjectured to be a reason because of care seeking or differences associated with caregiving behavior and so on. But the point is that often we'll have a structured situation where we'll have subtypes of people, sometimes in a hierarchy. And any logic provides a way with what's known as subtyping and inheritance to take that into account. You have one agent extending another type of agent. They are persons, but they're also females or they're also males. And as such, they could be put in a network of persons, but they have capacities and features that are unique to their particular situation. So women can, have certain, so they can give birth or be pregnant, and men would not. And we can capture these hierarchies of specialization, and in fact have networks of persons which are mixed of females and males, or have whole populations and whole spatial areas populated by these people that are mixed in this capacity. Okay, so this is one way. It's not the only way to have multiple types, but it's a way that plays to the strength of what's called object-oriented programming, in the sense that you can reuse mechanisms for person in any, in male and in female, without having to duplicate them as well. Okay, this is one way to have multiple types of people circulating. You'll notice, by the way, this model, I have a version of this in a compartmental model. And, oh gosh, it takes me back several years. A former colleague of mine, student of mine, and colleague now, Karen Yee, who's a dearly dear collaborator and friend. She's now with Alberta Health Services. But for her first modeling class with me, she decided it would be interesting to look at the interaction of HPV and smoking. She took this model from the paper, which is, 100 pages once you consider the supplemental material. It's a lot of material. And she put it into a Vensim model, which is a model for system dynamics, for compartmental models. And she subscripted it by smoking status, sex, sexual activity risk group, and one or two other characteristics, I think. It created this big mixing matrix. And it was unbelievable to see what she was doing. Just incredibly energetic, but incredibly awkward. It just brought out all the difficult features of operating with a compartmental model that's highly stratified. You had progression of people along smoking status and progression of people along HPV status, and broken down for different types of risk behavior. And oh man, I can't believe she did that for the model. I mean, it's unbelievable. But in any case, she later helped oversee the conversion of this to the agent-based model you see here. And that model is just so much cleaner. I know this looks big. I know it looks fearsome and so on. But believe me, it's just so much, it's incomparably better and more understandable here, and easier to describe, easier to understand, and it supports clear network connectivity and potentially changing networks, much higher resolution in terms of the questions that we can ask about some of the interventions involved. And we can look at other types of phenomena that just would not have been practical with the original model. So I think of this as the Karen Yee model, and we need to get this thing published because so much time went into this, and unfortunately she moved on to Alberta Health Services, but we haven't yet gotten a paper out the door on this. So anyway, I share it with all my boot camps, and it's a nice little example. Okay.
So with
Yeah.
those populations and
Yeah.
how would you create that just in a simple form? Like, do you create new classes of agents for the female and male, and then how do you
Right.
connect them to the people?
Great question. And to be honest, I'm going to have to go back and remember this. So if we go to Maine, there's only one population here, okay? And this population of people gets populated by, initially, you'll note, its initial number of agents, 0, okay? And if we go search for population here, okay, well, yeah, we'll find a certain number of references to it. But one of the things we will find here is, we will find a situation where people are added into this model here. They're added into the model here. We go through a normalized population and we basically add new males in, or we add new females. This is and I try not to show these to my students lightly. This is the type of stuff that could be put into an advanced boot camp like we offer in August, or intermediate level boot camp. But it turns out each agent in any logic has what are called, well, they have extra things you can put into them. And one of the things is code that can run when the model started, okay? Or when this agent comes into being, it can run certain types of code, okay? And basically, I wouldn't do it the same way this way. I'd do it through an event. Older man and hopefully wiser now. But here on the startup of the whole model, we add in a certain number of people of each type. So we have this normalized population, which is broken down by sex, ethnicity, and risk group. And we add the requisite count of people into this model. So we go through each sex, each ethnicity, each age group. Yeah, so it's sex, ethnicity, age group. And for each of those, we loop through the number of people of that type in the population, and we add those people into the model. Okay? In other words, we have a specification of how many people are there in the population in different subgroups, and we just loop through and add them in with that number of people. And then we initialize certain aspects of their behavior, etc. So we set their initial smoking state and sexual activity. Okay? So this is an example of adding a certain number of people at the start of the model. We do this add new male, and add new male essentially, well, it adds them to the population. Okay? Is that helpful? Yeah. Okay. Any other questions about this? This is an advanced model for sure. This is a very advanced model. Sorry?
You read that in from a data set?
I'm not sure. I can't remember exactly where this is from. It could have been read in for other models. We can reread that sort of thing in from a database. This is read from a file or read from a database. I think normally for the models I provide, I see. So,
Don't worry.
For models I provide, I try to avoid them depending on databases, just because my students won't have access to databases, and so I try to make them self-contained. But we do have a number of models that have run extensively using databases to store assumptions about scenarios, or to store the information to initialize the model, or to store the results of model runs. And it's a good practice. We like it. I prefer doing it to storing things on disk. It's just that one of the things we found for our boot camps is that it can be awkward to have a database, because then everyone in the boot camp has to connect to the database, etc. Okay, So a little bit awkward for that. Happy to answer any models about that, any questions about that. I'm going to close this model, and I want to go to another model, which is going to be, let me go get this one. Right. So this would be in the hybrid models area, and this model is a CTL state variable model. Okay, CTL state variable model. Now, this model was based on some work I did in what we called immunoepidemiology, and it seems to be a term that's stuck in the field. But basically, we're simulating the immune dynamics of an individual over time and placing them in an epidemiologic context where that immune dynamics affect